Hey guys, welcome back to my channel. Just check, let me check if this. Hey guys, okay, great. So today is the third video of the series about algorithms. I was studying from educative. The course I'm doing is ACE the Python coding interview. I was working on graphs. I've done from the last time where I did, I think the first challenges about graph. I did also other challenges here. Some of them were easy, others were pretty, like a bit more complex than usual. Now we missed just two challenges to finish to reach the half of the graph part, and after we have clone a direct graph, minimum spanning tree, blah blah blah. These are standard problem you will get in a coding interview. The challenge 7, but I'm at challenge 7. Honestly, from this moment on, problems start to get a bit more complex. Maybe it's the first time I'm doing some of them, and even though I know what is a minimum spanning tree, I don't remember, for example, how to solve this type of problem. So it might take a while for these problems to get solved. So let's start. I'm starting from challenge 7. Check if a given and directed graph is a tree or not. So, for example, we have this sample. This is a tree. This is not a tree. So what we could do, we could write down these two graphs and try to write a function that is able to establish if a given graph is a tree or not. In general, in order to be a tree, a graph shouldn't have any cycle, first of all, and from the root node we can reach any node in the graph. So the idea is that starting from the root node, using breadth first search or depth first search, we should be able to reach each node. Plus, we have to double check that for while we are navigating through the graph, we don't get into a cycle. So we don't get a node that has been already visited. I would say yes. So if a node that has been already visited gets visited a second time, it's not a graph. It's not a tree. So let's go. Let's start. So as always, I use the Studio Code and PowerShell to run the problems. Okay. Yes. Okay. So we start from defining the function main. We create two type of graph. So graph 1 equal, let's see what we will put here, and after we will have graph 2. So we need to create a node class, node equal, so now I'm defining the node class. This is the constructor. Item, just data equal data cell dot neighbors equal empty and self dot is equal false by default. Let's go to check how the trees are supposed to be 0, 1, 2, 3, 4, 0, 1, 2, 3. Okay, so we need 4 nodes. So we have 4 nodes. We have node 1, node 2, node 3, node 0. 1, 2, 3, 4, 5. Okay, so we have node 0 and we need to add even a depth add self node self dot and node. Okay. So 0 dot node 2, node 3. I was the 1, 2, 3 and 3 as a name of node 3. Node 4. Okay, so this should return true. If I create this is our presentation of a graph. So we put the graph in we represent this as an array of nodes, a collection of nodes, let's say. So it just helps us to know which is the right number of nodes we have. So in case a node is not reachable, we should know that it's not reachable, so it's not a tree in that case, okay? And we have graph 2, which is going to be more or less the same, 0, 1, 3, okay, but let's do it later, so we just invoke is a tree root, that's the root, which is node 0 in this case, and we do the print of the result, print of this result, and is a tree. So the is-a-tree method needs to verify a couple of things. That given the root, we should be able to reach all the possible nodes in the graph, and after it has also to check that there are no cycles in the graph. So we could do it using breadth first search, which I think is the easiest. But since I'm not very I noticed I'm not very good implementing that first search, maybe because it's recursive, I will try to implement this problem using depth first search as the approach to navigate the graph. So first of all, we have to know if a given node is able, starting from a root, we can reach each node. So assuming actually this graph, no? Where the node 0 is the root. Let's assume this. Okay, so we do that. The length of this graph is our this is an array where we keep the fact that to keep track of if a given node is reachable or not. So false, blah blah blah, times list graph. Okay. This is our visited, maybe not visited, let's say nodes, node visited, yeah. So, okay, so that first search. So the idea is that starting from the given node, we take all the neighbors and we check if we check all the neighbors, and every time we check the neighbor, we update what it returns is this array of visited node, which will be updated with the nodes that we managed to reach going through that specific node. In this way, at the end, we will check if the node visited are all true. If that's the case, we return true. Otherwise, we return false because some nodes will not be reachable. Plus, so the idea is that this will be passed as a reference, so we will update this array while we go navigate through the graph, and so we don't need to return this, but we need to return true or false in case there is a cycle or not. If while we were navigating through the graph, we discovered that there is a loop, we return true. Otherwise, we keep returning false. So the idea should be that, let's do something like this. Graph, this is the root, no? By definition, this is the root. We define this as a root. So for neighbor input dot neighbors, we invoke the address of neighbor and node visited. If this returns true, a cycle. Otherwise, we keep going, and we return if node dot count true is equal length of this graph. Okay. And also we specify that the route has been visited, for example. So first of all, we check if a given node has been already visited. In that case, we are not in a tree. So if root of this is true, is equal to true, this means that return false. So if return false. Otherwise, so if not is equal to, if that's not the case, it means that we can do this. So not visited in position root.data. This should be equal to, because we are visiting this. And for neighbor in root.neighbors, so we do DFS of neighborhood node visited. I'm doing something wrong here, I think. So if if not visited, the root.data return false. Okay, not visited, we set it to true, and for all the neighbors we search. And after we invoke DFS again. But that's not correct, because we have to return false. Let's do this. For memory root nodes, we're gonna call this, okay, because we want to get this updated. We have just to return if there is a cycle. When there is a cycle, when a node that we visited already, return data. Otherwise, we return a trough. But if we return a true, it means that there is a cycle. So I'm doing something wrong here. So these two methods need to talk. If underscore DFS not visited. Let's say that DFS tells you if it's a tree, no? So if this is not visited, blah blah blah.
if DFS return true, so that means there is a cycle because we return true. Otherwise, if all of them they don't return true, we just return true. So let's go through another time. So I'm okay. I received the list of the graph. I take I save an array where I store if a node has been visited or not. From I take the first node, the root, and from this root I cycle through all of my actually. You know what? And I invoke this here, no? So, and I invoke the DFS on the root. And the DFS is going to tell me if there is a cycle. DFS, like DFS is a valid tree. Let's call it this way, no? So this is going to tell me if it's a valid tree. So let's do that. DFS no, DFS as cycle. What's the cycles? DFS as cycles. So the DFS as cycles is gonna tell me if there is a cycle or not. If there is a cycle, we return first. Otherwise, we get not visited, and if all of them have been reached, it means that we have a valid tree. Okay, return false. So here we do def, DFS as cycle, root not visited, and not visited, root.data, return true. Okay, because if the node has been already visited, it means that it's not a tree, there is a cycle, or so we return true, and as a result we return false. Otherwise, we get it visited and we cycle through all of them. If only one of them returns true, we just return true immediately. Otherwise, we keep going, because if we keep going, what is gonna happen is that at certain point if it's a valid tree, we are gonna go blah blah blah, and we will reach a point where we will not have neighbors because we are in a leaf, and so we return false. Since we return false, we are gonna be here, and so this will skip the return true. And if for all of this it's true, so for all the nodes in the graph it's true what we are saying, we are gonna have the return, we are gonna return false at the end. And so at that point we could check if counting the true makes the given graph a tree or not. So this should work, but maybe I'm, forgetting something. Most probably, who cares? So we do Python graph blah blah blah. So has no len. Node has no len of list graph. List graph. Graph 1, sorry. False. This was supposed to be a tree? Yes, it was supposed to. So it means that at certain point we you know why? Because I think here I'm doing this, so this shouldn't be done here. See, indeed, it's true. Nice, good. So now if we do the same, but instead of using this graph, we create another graph which is gonna be like the second one. So we have 1, 3, and the 2 is connected to the 0 and to the 3. So and node 2, okay, and node 3
is connected to node 2. So it means that node 2 has been touched by both of them. And we have node 4. We don't have node 4 in this case. Let's try. False in this case, but so it's false, that's correct. But let's try another one. So let's try the approach of before, so with the node 4, etc. So node 0, node 3, node 4, but we add a fifth node, which is at the touch, and in this case we add it to the graph here. So in this case we should get that this is not a correct tree, because from the root you cannot reach all the nodes. Indeed, if we remove the node 5, for example, should be get back to true. Done, over. So this is done. We can go to educative and click on completed. Next. Yeah, most probably the computational cost is ODN plus V, which are plus E, which is the number of nodes plus number of edges. That's it. Challenge 8. Find the shortest path between two vertices. Okay, this can be found using this can be found using several algorithms. The dummiest one is to I don't know. Let's go to the solution. Let's see. Because this is a well-known problem in computer science. So it's how do you find the shortest path between two nodes in a graph? This is what Google Maps does every time you search for a place. The review provides a tenant, blah blah blah. Okay, once again, breadth search come to the rescue. The visited list must be familiar to you by node. The paragraph lies in distantly. For each node, the index value is additional. Show the node's distance from A in terms of the number of edges where A. So in this case, it uses breadth first search. We can even use depth first search at this point. The only problem, I think, is that instead of flagging the visited node, we just need to don't flag anything, keep adding them to the nodes, and in case actually instead of visiting we should update a flag which tells what is the shortest path. In this way we know that is the shortest path. So that's it, more or less. We could do it through breadth first search and depth first search. Anyway, there are other algorithms like Dijkstra, things like this. But yes, that's it, I would say. Solution review, find the shortest path between two vertices. So, okay, so let's go with this one. I think we've done half an hour so far, so let's go with the next one. So I would keep the same structure of before. So we just remove this function, which is not what we want now. And we keep the same graph as well. And we search for the shortest path between two nodes. But we have a path. Node 0, for example, and node 4. Okay. So let's assume that each node we step into is a hoop. So, for example, for example, in this case, 0, 1, from 0 to 1 is 1 hop, from 0 to 2 is 1 hop, from 0 to 4 passing through 2 is 1, 2 hop, from 0 to 4 is 1, 2, 3 hops. So the fastest to go to the 4 is passing through the 2. So 1, 2, 3, 4, 5, we have all of them. So 1, node 0 to node 1, from node 0 to node 2, from node 0 to node 3, from node 3 to node 5, and from node 5 we go to node 4. From node 5 we go to node 4. And from node 2 we go to node 4, node. We don't need this time, just need the nodes which are collected by the between themselves. So depth shortest path between two nodes, node 0, node 4. Let's go. So if node 0 equals 1 or node 4, wait, let's call it root and distance. Root for distance equals none, root equal none. If both one of these is none, we just return minus 1. No? So instead, if we could do something like this, we need to have a queue. If we are going to use from connections import the queue deck, as Pythonist says. The queue of an empty list, it will be our queue. We will add to this queue queue.add. We will add our root, and while the len of the queue is more than 0, we just do q.pop, no, sorry, q dot pop, in this case pop left, and this will be our current node. For this current node, we go through all the neighbors, or we will have also distance equals 0. No? Every time we pop something, the distance will increase by 1, if we are stepping into a node. So for current node, blah blah blah. So for current node dot neighbors, we will have a neighbor, and if so in this moment, every time we hit someone of the neighbors, we reach that neighbor. So in case the distance is less than what we observe, so instead of this, that we use distance from root, which is gonna be math.inf. We do int math. Okay. So but at the same time we will add it to the q dot append neighbor. Okay. Yes, makes sense. But there is something wrong here. There is something wrong because the distance is we start from distance equal 1, for example, because we stepped into the root. So we pop out something and we check. So starting from that node, reaching the other is distance plus 1, and we update the distance. So each time we are on a node, we have the updated distance, I would say. So yes, this is correct. The one I put before was wrong. Q.append in neighbor, okay, because we have to add it to the queue. So once we have added this for all, we check okay, and the distance is equal 1. Okay, no. Do something like this, current node dot distance, and here we'll do that for the root dot distance equal 1. Okay. So the idea is that we set the distance of root to 1. So once we get into it, we get current node neighbor dot distance is greater than current node distance. So 1 plus 1, yes. In that case, we do current node distance plus 1 as the distance from root for the neighbor dot distance, and we go okay q.append. Okay. So shortest path between two nodes. So as soon as we found it, as soon as we found okay, so root instead of distance, here we have destination. So destination equal this. So well, in this way we will find the distance to destination. So we will just return destination dot distance. Let's see if it's gonna work, my friends. I didn't save it. Shortest distance graph.py. So let's go to run it. Error. It's not defined, and maybe because I mistyped something. Yeah, and it wasn't. Yes, has no attribute. Append. There is append. Distance. Let's go distance. 3. Makes sense. So y was 3 was correct. Let's go to check. So 1, 2, 3. Yes, it takes 1, 2, 3 to go. In this case, it was taking 1, 2, 3, 4. Here it says 2 because maybe it doesn't count root as a step. So if we do something like this, maybe it's gonna be like 2. Yeah. So said that, what we do now. Well, it's working, but let's see if it really works. So if we, for example, from node 2, instead of going to node 3, we add a new, we go from node 2 to node 5. Let's see what happened. Now it should be 3, indeed, because we passed through the 3. Through the
five node. So, but let's try to put between node 4 and node 6. And after from node 6, we will add neighbor node 4. So let's try again, but with the node 6 added. Yeah, that makes sense. Okay, so that's it. I completed even this challenge, so let's go. And so we are done with the standard challenges with explanation. So now we will have other, let's see, what time is it? I can try to do another one. Clone a direct graph. I don't like this honestly, but the idea is that given the root node of a direct graph, clone this graph by creating this deep copy so that the clone graph has the same vertical and edges than real. Let's look at the below graph in blah blah blah. We are assuming that all are reachable from the root vertex. We have a connected graph. Okay. Ints, use hash table, use depth first traversal. So I think here what it says starting from the root node, you can use that first search, that first traversal to traverse all the nodes, and for example, from like I think you want to store in an hash map. The key is going to be the node, and the value is going to be an array where you put all the edges for that given node. So, for example, well, you can even use breadth first search here. It's not breadth first traversal. I mean, we can use that first traversal just, to challenge ourselves, because honestly I find that search a bit more complex than breadth first search. But that's my opinion. This so from that, what we could do, we could get all the neighbors. For all the neighbors, invoke depth as well, and we add a thing in the hash map, and we pass the hash map to the recursive function, and we keep updating this map. And in this way, we should finally have everything. Yeah, that's done. So we guess we need to start. Yeah, let's see. And I drink a bit of water. So let's keep the same structure of before in terms of node and methods. Here, what was the name of the challenge? You see, direct clone graph. Clone graph. Clone.graph. Okay, works even with that. Okay, so here we just clone, and the clone should return us maybe the root node, new root. And here we will put just a breakpoint, because instead of create a function that prints everything, we could just check out which are the neighbors of new root and see if they are the same of our graph. So let's call the clone root, and here we could call it mark. Okay. So we do something like this. So the idea is to use that for search, okay? So the idea is that if root equal none, we just return none. No, we just return, yeah, none, because we did our job. We did what we were supposed to do. Otherwise, if root is not none, what we do? We just go through all the neighbors of root. So first of all, we add to the map dot data equal we could do something like this. Something like this. Okay. Once we have done this, we go for each node in root.neighbors, and we invoke a clone of that, but we pass node and the map. Okay. So at certain point we will reach, but of course if we have cycles, it's gonna be a problem because we will be always but I think to avoid this could be that if map blah 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 dot get of root dot data is where if it's not there we just return false. We return yes false equal false. So we don't get it. In this case we just return so let's go through the okay. So if root is equal none, we return none because makes sense. If map.getRoot.data false, so the element we are looking for is already data is there. If it's not there, it's equal false. So we have to keep going. But if it's there, so it's different from false. We just return because we don't wanna go through again to a node we have visited already. Correct? Correct. So otherwise, in case we are not in that scenario, we do all of this, we clone for all of them this, and we return ourselves. This, no, that's wrong. That's, let's do it something like, let's return the map. Okay. And we do something like this. That clone of root. Okay. And we clone root on map. And after this we do for key in key value in map. So in this way we reconstruct the items, we reconstruct the graph. For now, let's leave it like this for now. And let's see if in the map we have what we want, okay? Because there is a problem of pointers there. To again, clone, okay, this makes sense, blah blah blah. Okay, that's it. Zero, 1, 2, 3. Okay. Because here maybe I'm going to drop. Okay. Okay. So 1, 2, 3. 1 more children. 2, 5. 5, 6. 6, 4. 4 nothing. 3, 5. Let's see if it was as yes, it was like before, no? Okay, so makes sense. We have the map, so we managed to clone it. Now we have to find a way to reproduce this. The problem I had in this for loop was that I was creating different objects for the same nodes. So if a node has been referenced twice, I was not able to keep with me that information. So, but anyway, what we could do is for key in values, blah blah blah, we do graph. We do a graph. We do node key, and we do new graph in position. len of map.items, map.keys, and we do that new graph in position map in position key is equal to okay. Let's see if it works. Map.keys like this. So if we do the graph, 1, 2, 3, 4, 5, 6, 7 nodes. Nice. So we have 7 nodes. 0, 1, 2, 3. Yes, which were the one we created. So now, if we go for again this way, so for being values, we do that for new graph in position. We add the neighbor, but we add the neighbor which is new graph in position. In position B. So here we should have the values. We should have an array which represents our new graph. Copy, paste. So let me check. New graph in position 0 is our root, so data should be 0. We should do dot neighbors. We have 3 neighbors, which they should be 1, 2, and 3. 1, 2, and 3. And most probably, if we do neighbors of 3, we should find 5. 3, not 3, not 3, see, not 3 as neighbor 5, so let's go. Neighbors 0, data should be 5. Yeah, so this works. So what we return, since we said we just need to return the root, we do graph position of 0, which is our root. So just return this, and that's it. This is over. So it's 1 hour. Nice, good job, Ricky. So okay, new root. Okay, so if new root should be 0. Data equal 0. So node 0 dot neighbors in position 2, for example. No, position 1 dot data of neighbors. Let's move to yes. Position 0, but the data should be 5. Okay. So, if instead of doing this, we do this, but instead of node 0, we put new root, we should get the same result. Indeed. This should be 2, accept. Okay, so yeah, it seems that it's working. Yeah, that's it. Let's close our shell, and we are done for today. So thank you for watching. I hope you liked this hands-on exercise I'm doing here. I think they are pretty interesting if you are willing to prepare coding interview. So
Anyway, I will keep posting for the next month since I started a new challenge where every day I will try to do at least 1 hour of challenges in this way with this focus. So that's it. Oh, but I was almost forgetting to select this. So this is over. Okay. So yeah. Later we will keep going with heaps, hash tables, arrays, heaps, hash tables, arrays. Yes, I will try to do them all before the end of the month of July, and after in the first weeks of August, I will try to do another challenge, which is more like grokking the coding interviews, which is another course on educative to prepare also that, just to be super under 100% sure. I will go over to all the algorithms questions so they can appear in a coding interview. So thank you for watching. Please leave a comment if you liked or if you didn't understand something. Press the thumbs up button just because you get cooler. And talk to you in the next one. So see you. Bye.